Hello, community! You remember reg and coding pushed to the side, and we have some new elements in AI that will generate new value for us. And yes, this is here a continuation of my last video, but today we look here at brand new research. And at first here we have from Argentina here, empowering domain-specific LLMs with graph-oriented databases. Yeah, and this is exactly what we are going for. And then we have here on the other side of the world, Hong Kong Polytechnic University Department of Computing, and they talk about here Neuro-Symbolic entity alignment. And you might say, what is this? Now, imagine you have two knowledge graphs. You have a biomedical knowledge graph and a pharmaceutical knowledge graph, and you want to combine here the insight and the data of both knowledge graph into one new knowledge graph to mine cross-discipline relationships and discover new patterns. This is what we are talking about. Plus, let's come back, Harvard University and Pfizer. And you might say, hey, what are they researching for? And this is just yesterday. So they talk about knowledge graph-based agents for complex knowledge-intensive question and answer medicine. So what they do, they take a complete knowledge graph now as an agent in our LLM, and they address here a specific domain medical queries from doctors in hospitals. So extremely interesting documents in themselves, but you know what? If you read them, and I highly recommend you read all three studies, you notice that they have a common topic. Let's have a look at the first one. Domain-specific language model and the graph databases and how we can integrate them. This means combining neural models with graph databases improve the explainability, it reduces the latency, and it boosts the performance of the complete system. The second paper is about here the Neuro-Symbolic framework. And the insight is here, this Neuro-Symbolic approach outperforms purely symbolic or neural methodologies in both the effectiveness and the robustness. And then finally, Harvard and Pfizer, they combine also the neural systems with the symbolic systems to handle real complex biomedical queries. And they go here, ensure accurate and robust reasoning and medical queries by verifying information against structured biomedical data, and they have this data in a knowledge graph. And the beauty now is we combine the reasoning capabilities of a symbolic AI system with the pattern recognition strength of a neural LLM. Let's do this. So here, I just give you the results. You don't have to read all those three studies if you don't want. Study 1, Study 2, and Study 3. This is the interpretation of the results. But for my green grasshoppers, you know, it is easy. We have an existing knowledge graph. Let's say this is our knowledge graph. The representation of our knowledge graph. And we want to apply logic, and we have additional data, and we want just to update our knowledge graph. So then we have this particular knowledge graph. And let's have a look how we can do this. Now, as I told you, we combine now the neural AI with the symbolic AI. Easy. Input, output, the rule and the check for my green grasshoppers. Now let's go for an example. Let's be here in biomedical research because more or less all three studies are about biomedicine. Imagine you have a vast collection of biomedical research paper, or go with any domain that you like. And you want to analyze and extract meaningful insights about some specific relationships. And you have your LLMs, and you have done this, and you have your symbolic AI, and you have done this. But now the question is, hey, can we combine those systems to have an added value? And it's an easy three-step procedure. We will ensure step 1, data processing with the neural models. Step 2, structuring the knowledge here with the symbolic systems. And then step 3, enhancing the knowledge graph with the neuro-symbolic insights. And I tell you the outcome. We will have an enhanced knowledge base, we will have actionable insights, and we will have a transparent system and a system that you can trust. Let's start with step number 1, pattern recognition. So we have a large LLM, transformer-based model, whatever you like, and this processes here the unstructured text to identify the entities, our objects, our nodes, our edges, And here we go with diseases, proteins, the interaction between biochemical components. We extract the information. Step 2 is a knowledge graph construction. So those extracted entities by our LLM, the relationships between them, are now brought into a new knowledge graph where, simple idea, the node represent entities, the protein, the disease, and the edge represent relationship between them, inhibits associated with all the attributes that we have in biotech. And rule application follows now. So symbolic rules are applied to ensure local and logical consistency in our subgraphs, and maybe also we are able to calculate here the complete graph structure. Step 3, enhancing now the knowledge graph with our neuro-symbolic insights. So using now the knowledge graph and the symbolic rules, either that we know in a domain, or, I will talk about this in a moment, we can deduct from the data. The system can infer new potential drug-disease relationships not explicitly mentioned in the text and not available in the literature. This is an example. Beautiful. Now, I know some of you told me here in the last video, hey, you were talking here about graph structures, but the pure mathematical graph, this is here on the right-hand side, is different from what you use here in artificial intelligence. And you are absolutely right. We use here the idea of the pure mathematical graph, and you have here the properties, but we add additional information. We store, we manage and query large-scale complex data here over our graph-based databases, over the graph itself. The data representation are in nodes and relationships with properties and labels. We attach here everything from tensors to property alignments. So you see, it is not the pure mathematical object, but we add value to this, we add information to the node and the edges. Okay, so learning now those logical rules, and this is one of the beauties of this system. You can extend now the symbolic techniques that we have in AI because it is an artificial intelligence system. So maybe this system now is able, given enough data, to come up with new rules, with new logical rules deducted from those data. I'll give you a simple example. We want to expand our previous knowledge graph and explore how new rules can be inferred from the data and applied here, and we build a better knowledge graph. So our initial knowledge graph might be this one. Alice is a software engineer. Alice works at a technology corporation. Alice collaborates with Bob. Bob is a data scientist, and Alice and Bob develop here machine learning models. And now we want the system to infer potential new collaboration based on existing data. So there are 5 easy steps. You have a data analysis by the neural component, or LLM. This simply means a pattern detection. Neural network analyzes existing collaboration and identify that individuals with complementary roles like software engineer and data scientist frequently collaborate on machine learning projects. Step 2, rule induction by symbolic component. So if a software engineer collaborates with a data scientist on machine learning projects, then they may collaborate with other data scientists or related roles. Step 3, inferring new relationships. Based on the learned rule, the system now predicts that Bob, this is a data scientist, might collaborate with Carol, a data analyst, on future projects. 4, updating the knowledge graph. So the neural network analyzes existing collaboration and identifies that individuals with complementary roles, like software engineer and data scientist, frequently collaborate on machine learning projects. And step 5, explanation. The symbolic reasoning. So Bob is a data scientist which collaborates with data analysts like Carol on machine learning projects, enhancing data analysis and model development. So you see, it's a rather simple way to come to deduct new logical rules. What does it bring us, this extended symbolic or extending the symbolic techniques? We have a dynamic knowledge base now. We don't have to do this manually. The system can evolve by learning from new data, reducing the need for constant manual updates on the logical rules. We have an improved decision making. These enhanced rule sets derived now from the original data, your domain data, can lead to more accurate and insightful inferences and maybe even detect wrong logical rules that you might have thought would be correct but are now simply outdated with the new data. And you have scalability and maintenance because you have automated rule learning, which facilitates a more complex and bigger, more large-scale knowledge graph here much more efficiently. So you see from our green grasshoppers, short summary, it is easy. We can deduce new rules from structured information. Remember, data information, structured information. Now we're at the rule level. We can discover new rules from those data, and this allows us this integration here, the interpretability of symbolic reasoning. So here you have the result. It is therefore logical to deduce that a combination of the pattern recognition in our machine learning, our neural approach, our LLMs, our ChatGPTs, with symbolic systems will significantly enhance the understanding and the management of complex and large volume of text data. And this synergy that I noticed here in these 3 papers just from 2-3 days ago, where all the research of these big corporations are now focused on, this synergy, often referred as the Neuro-Symbolic systems, leverages now the strength of both paradigms to address challenges that neither system of them could effectively manage alone. So, very easy. Your neural, the machine learning approach, the pattern recognition and adaptability of our ChatGPTs, and the symbolic, the rule-based approach for the logical reasoning and the structure. And now finally, I hope that we can detach here that our LLMs should also be able to do here the perfect logical reasoning when we have different tools that are so much better. That are simple tools that we can use here with, function calling or however you want to do this. So finally, we use the right tool for the right job. Great. Now I know that my green grasshoppers told me, hey, the last time you give us here a detailed example at the end of the video, can you do this again? Yes, I tried this now the second time. So a detailed example here for beginners for my green grasshoppers. Now I do this now on ChatGPT 01 Mini because I was asked not to do it here on Strawberry because you do not all have access to Strawberry and how you can do this on Mini. So I did some experiments, I had some discussion, and now I just want to show you here an example then in the logical deduction of 01 Mini. So I started then with a sample text, and John is a teacher at a high school, he teaches mathematics, and Mary is a student in his class. So this is the data that we have. Our goal is now to extract and structure information. So convert now this simple text into a structured format. And I told the system, hey, go with 2 options, either go with a JSON structured format or a graph-based structure. Then we will apply our neural systems. We will use pattern recognition to identify relationships and potential inferences. We will then apply symbolic systems. We use predefined rules to start with to enforce logical consistency and derive additional insight by applying here the symbolic rules, and then we will integrate everything into a brand new insight. We will combine neural and symbolic outputs to achieve a deeper understanding. Of course, this is just a demo. This is just a simple sentence. But of course, you can apply this to biomedicine. So here we go. Step number 1, extract and structure the information from the data that we have. So you see, the data is here, 1, 2, 3 sentences, and now we have information extraction. So we identify the entities. We have persons, John and Mary, we have roles, teacher and student, we have organization, high school, we have subject, mathematics and physics, and we have relationships. And you see, oh yeah, those will be our nodes and those will be our edges with specific attributes between the nodes. We have name, entity recognition, relationship extraction, everything our LLMs can do perfectly. Next step is then here, we have a structured representation of the information in a JSON format. Now, very easily, you see here typical JSON entities, ID, type, name, role, employer, subject, class. Beautiful. Or we have the option here to go alternatively, representing the same information as a graph-based format. And you have here exactly here this visualization of our graph structure. Now the next step, step 2, is now, as I told you, we apply now the neural system. This is our pattern recognition, our ChatGPT, our LLMs, whatever you like. Neural system, machine learning models, excel identifying hidden patterns, make prediction, and extract here some relationships from the data. So we have here a pattern recognition task, entity linking. Objective: ensure that the entities like John and Mary are correctly identified and linked to unique identifiers. Beautiful relationship prediction, sentiment analysis. And then we have B, our neural model output. Based on the input text, the neural model might predict additional relationships or verify existing ones. So prediction: Mary might also be interested in physics given that she is a student in John's mathematical class. Or the confidence score: assign probability to each inferred relationship to indicate certainty, or a probability distribution if you have some prediction classes. Step number 3 is now apply symbolic systems, the rule-based reasoning. Yeah? So we have predefined logical rules to start with to enforce the consistency or maybe derive new insights and ensure that the inferences adhere to domain-specific knowledge. Yes, there are rules, domain-specific rules, of course. So first we have the predefined rules, rule-based rules, employment rules, class relationship, and then we apply those rules to the knowledge graph, enforcing here the role-based rules, ensuring employment consistency, maintaining class relationships, yes, deriving additional insight. Using all those rules, the symbolic system can now derive further information. Now, inference 1 may be in our simple demo. Since John is a teacher at a high school and teaches mathematics, he likely holds a degree, some degree in mathematics or in education. Inference 2, Mary, being a student in John's class, may be enrolled in mathematics or in related subjects, not just in theoretical physics. Step 4, integrate now both the neural and the symbolic insights. Beautiful. So combining the outputs of the neural pattern recognition and the symbolic rule-based reasoning leads to a more comprehensive understanding here of our original text. So we have here a enhanced knowledge graph. After integrating here both systems, our knowledge graph, our structured data output format, becomes richer. We just integrate here the additional insights. B, explanation. The system can generate explanation based on those integrated insights. A and B, enhancing the query and the reasoning. And this is one of the reasons we have started all of this. That we have now a pattern recognition engine, our LLMs, and a symbolic engine for causal reasoning. And not everything is munched into an LLM. Beautiful. The tools and the technology involved. I had a little example, I had a little play here with my original strawberry. What you can use here, Spacey, here Stanford LMP, Hugging Face Transformer. We used here named entity recognition, here part of speech, tagging, dependency parsing. For the structured representation, I went here with JSON or with some graph databases or graph modeling tools here. GraphViz for the visualization is real nice. For the neural system, you just go with your ChatGPT or whatever you like. Plus, we have a graph neural network and the framework you do right in TensorFlow and PyTorch. For the symbolic system, the rule engines, you go either with them for semantic rules and logic programming Prolog for defining and applying logical rules. Integration platforms here, Neuro-Symbolic framework, you go either with Deep Logic, Noisy, or custom pipelines combining here this. And for the data pipelines, I like Apache Kafka, or I worked for 7 years now with Apache Spark for handling here the data flow between systems. Go with whatever you like. What are the benefits of this integrated approach that we have now? Pattern recognition and symbolic logic. Enhanced comprehension. Neural systems excel at extracting and recognizing patterns from unstructured data, while our symbolic system ensure logical consistency and adherence to domain rules. Flexibility, scalability, Neural models can handle large volume data and adapt to new patterns, whereas symbolic system can be updated with new rules as needed, or they can learn new rules given the current advances in artificial intelligence. Interpretability, transparency, symbolic reasoning provides clear explanation for inferences, addressing here this black box nature of many GPT models that are proprietary. Improved accuracy, robust inference. Great. So let's come to the conclusion. And now we start here, my little grasshoppers, from the pure data, from the pure text, 3 sentences. That's all we had. And then we move from a simple text. The AI transforms this simple text into a structured data representation. And in my examples, I've shown you here a JSON format or a graph-based format. You can go with other formats. And then on this format, we apply both the neural system and the symbolic AI system to achieve a deeper understanding of the content. And this new, beautiful neuro-symbolic integration leverages here the pattern recognition and the adaptability of machine learning models with the logical reasoning and interpretability of rule-based system. This enhances the data comprehension, ensures consistency, and enables sophisticated inferences that are both accurate and explainable. Again, what are the key steps? Short summary: we extract the information, identify entities and relationship, then we build structured data, extract the information down in JSON or a knowledge graph, apply the neural system, apply symbolic system, integrate both. And you see, this is now what we use, not RAG and not coding, but now we use here intelligent data fusion of pattern recognition and logical rules. And this brings me back here to the thumbnail of this video, where you see we are now focusing here not on the coding aspect and not on the retrieve aspect, but we are focusing here on a new topic here, how to add value to our system. And if Harvard and Pfizer are investing in this, hey, maybe it is interesting for us also to learn this. So practical implications: knowledge management, effectively organize and understand vast amount of textual data, intelligent system, develop AI application that can reason and make informed decision based on structured knowledge, not only LLMs. And then, of course, we have domain-specific application for healthcare, biomedicine, and this is the reason, I guess, why Pfizer is investing in this new technology. Now, if you go here, for example, to ChatGPT with Canvas and ask, hey, can you just provide me some basic Python code? So AI generates us here a complete example, text to graph AI analysis. You see here, yeah, it is absolutely possible to convert text into structured data such as JSON format or a graph, and then apply both the neural and the symbolic approaches for deeper understanding. So here's a breakdown how we do this. Again, text to a structured representation, JSON or graph, neural system application, ChatGPT, symbolic rule application, combine it. The necessary libraries that we need, and the Python code, and you have here on the right-hand side, within seconds, ChatGPT 4 Omni shown me here in the canvas here, this simple Python code. This is, of course, a simple demo. This is not a full-fledged code example. This just gives you a very simplified idea, but it will generate working examples for you. But of course, the real-world application, like Pfizer, they are much more difficult. But AI can already give you insight into the coding, into the understanding, and it's a beautiful starting point for you to further develop your ideas, your optimization, or additional intelligent steps that you want to add to this particular combination here of a pattern recognition LLM and a logical rule detection AI system. I hope you enjoyed it. I hope you had a little bit of fun. There are 3 great papers to read, and it would be great to see you in my next video.